Okay, it's time to work through some practice problems. And here we have 11 series that we're faced with, and we're trying to determine whether or not these series converge or diverge. And if they happen to be geometric, let's try to find the sum. Or we could find the sum if they were telescoping, but we didn't put any telescoping on here, so you won't see that. We're not emphasizing telescoping because it's not on the AP exam. So let's get started. The first one here looks to me to be a geometric series. And we could rewrite this to make it more clear that it's geometric by basically taking it as one fraction and writing it as -6/5 raised to the n minus 1. Then it becomes clear that your R value, or your common ratio, is -6/5. And because of that, we have a divergent geometric series, and with an R value, an absolute value of R that is greater than 1. Number 2, this one is also geometric. You can tell that we're multiplying the numerator by a -3 and the denominator by a 2. So I could rewrite this, or I could just say that this is geometric with an R value of -3/2. And since the absolute value of R is 3/2, which is greater than 1, this series also diverges. For the next one, my thought is here that the limit is not going to be 0 because I have a rational expression with the same degree in the numerator and denominator. And therefore, by the nth term test for divergence, the limit is not equal to 0, and therefore I can conclude divergence. Number 4 is tricky because we actually haven't taught you how to do this one, so let's see if we can puzzle it out together. What you can do is write an arithmetic series for the denominator here. We're adding 4 each time. So we start, it's like a line. We have a y-intercept of 3 and a slope of 4. So that is going to give me the nth term, 1/4n minus 1. And what happens with this is that it's not geometric because I'm not multiplying by the same thing. If I tried the nth term test for divergence, I would get a limit of 0, so that test is inconclusive. So the question is, do you have any idea if this converges or diverges? Well, this is going to diverge because it looks sort of like 1/n. I know it has a 4 here and it has a -1 here, but because it looks to be very similar to a divergent p-series, it will also diverge, and we'll teach you in another day how to do that test. Number 5, this is a p-series with a p-value of 1.5, which is greater than 1, and therefore this guy converges. Number 6, this is a geometric series which we can rewrite by factoring out of 4. So we'll have 4 times and then 4/5 to the n. So I've factored out the 4 here. So I have 4 times 4/5 to the n. And 4/5 is between -1 and 1. So this is a convergent geometric series. My first term, when I plug in 1, I get out 4/5. So that's 16/5. My R value is 4/5. I've already stated that this converges, and I can find the sum by taking the first term divided by 1 minus 4/5, and that simplifies out to 16. Number 7, we can do this one with the nth term test for divergence, because when you take the limit of this rational expression inside the natural log, your limit here is 1/2, and so the limit of the whole expression will be the natural log of 1/2. That does not equal 0, so this series diverges. Number 8 and number 10, these two I say go together because they're both geometric series. This is 1/e to the 2n, and this is just 1/e to the n. They are geometric series because when I basically can put this one in the format of 1/e² to the n, and my common ratio is 1/e². So each term I write out, I'm just multiplying by 1/e². Notice for both of these, numbers 8 and 10, if I took the limit as n went to infinity, I get out a 0. So this is inconclusive by the nth term test for divergence. But I do know it's geometric. It converges because this common ratio is less than 1. So I can actually find the sum, and my first term here is 1/e². And my common ratio is 1/e². If I need to lose this, it doesn't want to be lost. So if I have 1/e² minus 1/e², what I end up doing is, I'll write this out for you because it doesn't want me to show you. You have 1/e² divided by 1 minus 1 over e squared. You can multiply by e squared over e squared, so your numerator goes to 1 and your denominator goes to e squared minus 1, which is the sum of this series. Now for number 10, try again to see if I can get this to show, which it doesn't want to. Number 10 is very similar, and I'll write this one up as well. And I know I'm going out of order, but I feel like 8 and 10 go together. So this is also going to be a geometric series. In this case, if I plug in n equals 1, I find that my first term is 1 over e, and then each time I'm going to multiply by a common ratio of 1 over e. So my final sum will be 1 over e divided by 1 minus 1 over e. I can multiply by e over e, and I get 1 over e minus 1, which will be the infinite sum of this geometric series. All right, it's time to go back and talk about number 9. This is a p-series with a p-value of 1/4. So this is divergent because the p-value of 1/4 is less than 1. And number 11, this one looks to be like a harmonic p-series, but frankly, what you need to do to make this into a harmonic p-series is to factor out that 3 out in front here, and then just to have a 1 here. Then this becomes the harmonic p-series. And the harmonic p-series diverges, so if we triple all the values, that series will still diverge. So this one is, we showed here that the nth term test for divergence is inconclusive since the limit is 0. So it diverges because it's just the harmonic p-series times 3.